Now we move to the field effect transistor, the Fet. Recall that the bipolar transistor, the BJT, is a current controlled device. That is, the base current controls the amount of collector current. A field effect transistor, by contrast, is a voltage controlled device in which the voltage at the gate terminal controls the amount of current through the device. As compared to the BJT, the Fet is a very high input resistance, which makes it superior in certain applications. Two major types of Fets are the junction field effect transistor, the J-Fet, and the metal oxide semiconductor field effect transistor, the Mosfet. So let's take a look at the Jfet. Jfet is a type of Fet that operates with a reverse bias junction to control current in the channel. Depending on their structure, Jfets fall either into two categories, N channel or P channel. Diagram shows the basic structure of an N channel Jfet. Wire leads are connected to each end of the N channel. Let's get this up here so we can see it. Wire leads are connected to each end of the N channel. The drain is at the upper end and the source is at the lower end. So instead of having a base, a collector, and emitter, we've got a gate, a drain, and a source. Two p-type regions are diffused into the n-type material to form a channel, and both p-type regions are connected to the gate lead. For simplicity, the gate lead is shown connected to only one of the P regions. A P-channel Jfet is shown in diagram B. So we can see here the N channel, we've got N material with P material diffused into it, and we have the P channel with N material diffused into it. To illustrate the basic operation of a Jfet, the figure shows bias voltages applied to an N channel device. So let's see if we get this up here. You can follow through with the diagram. The VDD, which is kind of like the VCC, provides a drain to source voltage and supplies current from drain to source. VGG sets the reverse bias voltage between the gate and the source. The white areas surrounding the P material of the gate represent the depletion region created by a reverse bias. This depletion region is wider toward the drain end of the channel because of the reverse bias voltage between the gate and the drain is greater than the between the gate and the source. So you take a look at that, follow along with what your text says for each of the examples. Jfet biased into conduction. We can see what's going on with the meters here. We've got an adjustable gate source and we've got a fixed drain source, and you can see what happens. The greater VGG narrows the channel between the white areas, which increases the resistance of the channel and decreases the current drain. So you can see that in B. With less VGG widens the channel, which decreases the resistance of the channel and increases the drain current. Jfet is always operated with the gate to source PN junction reverse biased. Reverse biasing of the gate source junction with a negative gate voltage produces a depletion region in the N channel and thus increases the channel resistance. The channel width and thus its resistance is controlled by varying the gate voltage. Thereby, the amount of drain current, I sub D, can also be controlled. So they tell us, if we take a look at B and C, B, and C. It's just exactly that that operation here, where we're varying VGG and changing the gate, the channel, and the bias, and increasing and decreasing the drain current. J-Fet symbols, you can see below the schematic symbols for both N channel and P channel J-Fets are shown. Notice that the arrow on the gate points in for the N channel and out for the P channel. So we have that same pointing in, pointing out configuration as we had for the BJT. The Mosfet, or metal oxide semiconductor FET, is the second category of field effect transistor. A Mosfet differs from a Jfet in that a Mosfet has no PN junction. Instead, the gate of the Mosfet is insulated from the channel by a silicon dioxide layer. The two basic types of Mosfets are shown in depletion and enhancement. I'm just going to kind of buzz through these. You can pull out your text and look at it and read through these descriptions. The enhanced MOSFET then is a type of MOSFET, operates only in enhancement mode and has no depletion mode. It differs in construction from the D MOSFET in that it has no structural channel. Here we can see the schematic symbols. Again, you'll notice the arrow pointing in and the arrow pointing out configuration, so you know what you're looking at. What's important here with MOSFETs is handling. Because the gate of the MOSFET is insulated from the channel, the high input resistance is extremely high, ideally infinite. The gate leakage current for a typical MOSFET is in the PA range, whereas the gate reverse current is typical Jfet in the NA range. So the input capacitance, of course, results from the insulated gate structure. Excess static charge can accumulate because the input capacitance combines with the very high input resistance and can result in damage to the device. So if you've ever done any work on your computers or any other devices, typically they have MOSFET devices in it, and you have to be very careful to ground yourself when operating them. And you'll notice that they typically come in static proof bags. MOSFET devices should be shipped and stored in conductive foam. All instruments and metal benches used in assembly or test should be connected to an earth ground. The assembler's or handler's wrist should be connected to earth ground with a length of wire and a high value series resistor. Never remove a MOSFET device, or any other device for that matter, from the circuit while the power is on, and do not apply signals to a MOSFET device while the DC power supply is off. Recall that a Jfet must be operated such that the gate source junction is always reverse biased. This condition requires a negative voltage gate to source for an N-channel Jfet and a positive gate to source for a P-channel. This can be achieved using the self-bias arrangement shown in the figure below. Notice that the gate is biased at approximately 0 volts by a resistor, RG, connected to the ground. The reverse leakage current, the current gate to source, does produce a very small voltage across the gate resistor, but this can be neglected in most cases. We'll assume that the gate resistor has no voltage drop across it. So we can see here that we have 0 on the device at this time, okay, for the gate. For an N-channel Jfet, the current at the source produces a voltage drop across the source resistor and makes the source positive with respect to ground. Since the current at the source equals the drain current and the voltage at the gate is 0, Vs, the voltage at the source, is equal to the current at the drain times the resistor at the source. The gate to source voltage then becomes VGS equal to VG minus VS, 0 minus IDRS. So essentially we have minus drain current times the source resistor. For the P channel Jfet, we can see the current through the source resistor produces a negative voltage at the source, making the gate positive with respect to the source. Therefore, the source current equals the drain current, and the gate to source voltage then becomes, now instead of a negative, a positive. In the following analysis, the N-channel Jfet is used. Keep in mind that the analysis of the P-channel Jfet is the same except swap polarities. So the drain voltage with respect to ground then, VDD, minus the drain current times the resistor. Since V sub S is equal to IDRS, the drain to source voltage then becomes voltage drain to source VD minus VS, which gives us then the relationship VDD minus ID times the sum of RD and RS. In this example then, find the drain to source voltage and the gate to source voltage, given that the current for the drain is approximately equal to 5 milliamps. So you can see that set up in the diagram here. The source voltage then, IDRS, is equal to 1.1 volts. The drain voltage then, VDD minus IDRD, is 15 minus 5 milliamps of current times 1 k ohm gives us 10 volts. Therefore, the voltage drain to source is equal to the difference in the voltage at the drain minus the source. Gives us 8.9 volts. Since the drain voltage is 0, now we have voltage drain to source is equal to VG minus VS. 0 minus 1.1 gives us a minus 1.8.